Welcome back to the Deep Dive. Our mission here is to take the sources, all the complex research, and turn it into, well, immediate and reliable intelligence for you.
Today, we're jumping into a deep dive that really hinges on a surprising contrast. When we talk about AI, data analysis, fintech.
Yeah, you immediately picture code, algorithms, servers,
Yeah.
all purely digital things.
Exactly, purely digital.
But what if the secret to building the most reliable digital systems?
Hmm.
What if that secret doesn't come from computer science, but from, say, the factory floor?
That's the story here. Our sources today lay out this fascinating journey of an analytical system designer who brings the really demanding no-fail discipline of heavy industrial engineering.
And we're talking about things like mechanical engineering, quality control, even fire and safety.
All of it. And bringing that discipline to the architecture of modern code.
So it's not so much a career change as it is an evolution.
It's absolutely an evolution. This individual went from supervising maintenance on these massive, safety-critical physical systems where, a failure isn't just an oops, it's a potential disaster,
Right.
to architecting logical systems in the digital world. And the common thread through all of it is applying this intense engineering clarity to data that is, by its nature, ambiguous.
So our mission for you, the listener, is to really get how this works. We're going to unpack the key mappings, showing you kind of line by line how the skills of a quality control inspector
Become the skills of an expert in logical bias analysis.
Exactly. It's this disciplined, structure-first approach.
And you should care, because if you rely on data systems for, well, anything, running a business, managing investments, you need to know how to build a system that won't crack under pressure.
Okay, let's unpack this. To start, we really have to look at the foundations.
Yeah.
This is built on quick fixes. It's built on some serious academic and industrial rigor.
Absolutely. To get why these analytical systems are so objective, you have to look at the engineering background that anchors the whole approach. We're talking about a B.Tech in mechanical engineering with first-class honors.
Okay.
And that's coupled with diplomas in automobile engineering and fire and safety engineering.
That combination is really interesting. I mean, mechanical engineering is tough enough, right? All about structural integrity. But then you add automobile engineering, complex systems, and fire and safety. That last one feels unusual for an AI architect. How does that fit in?
It's all about risk management. I mean, fire and safety engineering isn't just putting out fires.
Well,
It's about designing systems to prevent catastrophic failure. You learn to spot the single points of failure, you build in redundancy, you enforce protocols where there is absolutely zero tolerance for a mistake.
then when you bring that to fintech,
It becomes your defense against data corruption, against logical failure. It's the same mindset.
so a mechanical failure could shut down a port. A logical crack in a data model could cause an equally catastrophic financial failure. It's a direct mapping of risk.
Precisely. And this wasn't just academic. It was immediately tested in these high-stakes jobs, like supervising safety-critical maintenance systems, designing preventive maintenance logic for places like GEW Contract and VOC Port Trust.
I can just imagine the pressure, supervising that kind of machinery at a major port. You can't just say, oops, my maintenance schedule was a bit off.
No, you can't.
So that discipline, that rigor, it teaches you to treat a data system with the same structural integrity you demand from a crane or a turbine.
And that's where the terms engineering clarity and architecting intelligence really come from. The big lesson from industry is that reliable output requires a reliable process. You just can't afford guesswork.
So if you drag that requirement over to the digital world, what's the end result?
The result is you build analytical frameworks that aren't just accurate. They're transparent, objective, and non-repainting.
Okay, that last term, non-repainting. That's a big one we need to define for you listening. What does that mean in practical terms?
Yeah, it's crucial. Think of it like a certified ruler. If you measure a piece of wood today, it should read the same tomorrow, right?
Assuming the wood hasn't changed, yeah.
A non-repainting system means the historical output for a fixed input never changes. A lot of systems will sort of retaint their own history. They adjust their model with new data, which can make past signals look better or worse than they really were at the time.
So an industrial engineer wants the pressure gauge to read the same every time, and they demand that same stability from their digital analysis. It's about trust.
Exactly. Trust and accountability. And that structural integrity. That's the bridge to the core philosophy here.
Which is summed up in 4 powerful words. Structure precedes insight.
It just flips the usual big data approach on its head. This idea that you can just, dump a mountain of raw data into some algorithm and wait for a perfect, trustworthy pattern to pop out.
It's unreliable.
Fundamentally unreliable.
It sounds more like designing a defensive system, not just a predictive one.
That's it. Order isn't just found in data, it has to be designed. That's the core identity of this AI analytical system designer. They build these complex, rule-based logic models where no template exists. The first job is to engineer a robust structure around the chaos.
You're turning market noise into a calculated, measurable process, which is why that professional tagline is so clear. Structuring intelligence from undefined systems. It's not just analyzing, it's building the whole framework.
And you see it in their other phrasing too, like designing analytical systems where no blueprint exists, or engineering clarity from raw, complex data.
So if you, the listener, have ever felt just overwhelmed by unstructured data or market noise, that feeling of paralysis,
Yeah.
this is the way out. You don't chase the insight first, you build the blueprint first.
Which brings us to, I think, the most compelling part of this whole story, the direct functional mappings, how these industrial jobs become the logical ancestors for these high-level analytical functions.
This is where it all clicks.
Yeah, these are the real aha moments.
Okay, so let's do the first one. Maintenance to architecture. In the past, the job was designing preventative maintenance logic for, say, a massive crane. Physical reliability.
And that exact same meticulous approach now goes into architecting intelligence in the digital world. The goal is identical, just the medium is different. You're not preventing a mechanical failure anymore.
You're preventing a logical failure.
Yeah.
You're stopping system noise from getting to the decision maker.
It's the same cognitive muscle. You have to understand the internal gears of the machine, whether it's made of steel or code, to make sure it runs predictably under stress.
You have to anticipate where it's going to break.
Our second mapping is maybe the most powerful one, quality-controlled bias analysis. This is all about that discipline of hunting for deviations.
So walk us through the history on this one. As a quality control inspector at Emirates Steel, what's the job?
Systematic inspection, quality assurance. Conducting these incredibly detailed inspections to find physical deviations from international standards. We're talking microscopic flaws, chemical imbalances.
And this work led to a real measurable result, a 10% reduction in defects.
Yes, a tangible outcome.
But wait, isn't finding a tiny flaw in a piece of steel totally different from finding a subtle bias in, I don't know, a million data points? Where's the common ground?
The common ground is systematic scrutiny and boundary testing. As a QC inspector, you don't just look at the steel. You put it under stress. You find out exactly how much load it can take before it fails.
Ah, so in the analytical world, you're not testing a physical load. You're testing the logical reliability boundaries.
You got it. They apply that exact deviation hunting mindset to bias analysis and logic validation. They're looking for the logical cracks in the data models. A bias is just a systemic deviation where the model starts to favor one thing over another.
So the QC inspector makes sure the steel beam is fit for purpose. The system designer makes sure that digital insight is fit for purpose under market pressure.
Right. And there's a third mapping here, too. Process monitoring to analytical efficiency. Before all this, they were an ETPRO operator.
That's effluent treatment plant and reverse osmosis.
Yeah, using data to monitor water treatment processes.
And the goal there was?
Operational optimization. Using real-time data to find inefficiencies, which improved the plant's performance by about 15%. It wasn't guesswork. It was precise, rule-based optimization.
So the input changes from water parameters to market signals, but the process of structuring data for efficiency is identical.
And you see the results in the current work.
So where does all this industrial-grade logic land today? The sources point to its application in fintech as an AI tech analyst.
And the specialization is really focused. Architecting market intelligence by converting that market noise, the messy, chaotic price behavior that just paralyzes most people.
And turning it into structured analytical insight.
They're building decision systems out of raw uncertainty.
And how does this show up in the day-to-day work? It sounds like it's a highly automated system.
That's where the efficiency comes from. A relentless focus on workflow automation to reduce manual dependency. I mean, high reliability means minimizing the places where human error can creep in.
So where does modern AI fit into this very structured, rule-based world?
The AI is not a black box spitting out answers. It's a validation and refinement tool. The sources talk about collaborating with AI platforms to refine logic accuracy to build more validation layers. The human designs the rules. The AI helps stress test them.
We see specific tools mentioned, like TradingView and PineScript. For you listening who might not know those, how do they fit in?
PineScript is the coding language for TradingView. It lets you write your own indicators and strategies. So this system designer uses PineScript to translate their industrial-grade rule-based logic, the structure, into back-testable code.
So it's the tool that turns the engineering blueprint into a functioning digital machine.
That's the perfect way to put it.
And the result of all this is pretty compelling, an approximately 25% improvement in analytical efficiency. That's a huge validation of this whole system-first approach.
It's proof that this kind of reliability, born from physical discipline, it transfers perfectly into the digital world.
To really synthesize all this, let's use the skyscraper analogy from the sources. I think it pulls everything together.
Yeah, it's a great one. The engineering degrees, mechanical, fire, and safety, those are the deep concrete foundations. The structural strength and risk management that lets the whole thing stand securely.
And the quality control experience.
Yeah.
Hunting for flaws in steel.
Yeah. That's the rigorous safety testing of every single beam, making sure every component is perfectly calibrated and reliable before you build on top of it.
And finally, the AI analytical system design work now.
That's the sophisticated electronic nervous system, the automation, the logic layers, the part that lets the whole building function intelligently and produce those reliable, non-repainting outputs. The modern tech only works because of the industrial discipline underneath.
So if you connect this to the bigger picture, the reliability of our modern intelligence systems really comes down to human-designed structural discipline. That's a lesson learned from industrial safety, not just software. And the key takeaway for you is that whether you're managing machinery or data, the principles are universal: precision, reliability, and structured logic.
It's the difference between hoping for certainty and actually designing it.
This raises an important question for you, the listener. If order has to be designed instead of just found, what are the safety-critical maintenance checks you need to build into your own decision-making systems to make sure they run reliably when the pressure is on?